Now that we have an understanding of basis vectors, let's define standard basis vectors. Standard basis vectors are the simplest and most commonly used basis vectors. To show how basis vectors simplify computations, let me give you an example. And again, in two-dimensional plane. We have a vector u, and we want to write it in terms of a set of basis vectors. Let's choose two arbitrary basis vectors. Remember that you can choose any two vectors that are linearly independent as basis vectors in a two-dimensional vector space. In this case, our basis vectors are b1 and b2. Now, let's try to write u as a linear combination of b1 and b2. Here the problem is finding alpha and beta. To find them, we need to solve a system of linear equations, which we will cover later. But after solving the system, it turns out that alpha is 1/2 and beta is 5/2. You can see that this computation isn't that easy, especially in higher dimensions. Now let's see how standard basis vectors make computations easier. Standard basis vectors are unit vectors along each coordinate axis. Usually we show them with letter E and with a little hat. Now let's write down u in terms of E1 and E2. Again, we need to find alpha and beta. But this time, because of our basis vectors, computations are much easier, as you can see. Alpha is the first coordinate of u and beta is the second coordinate. Now let's take a look at the properties of standard basis vectors. The first property is that the standard basis vectors are unit vectors along the coordinate axes, as we saw in the previous section. Therefore, they have a 1 as one of the components and zeros as other components. The second property is that all standard basis vectors are orthogonal. Orthogonality implies several applications in linear algebra, including linear independency, simplification of computations, and etc. The final property which arises from the first two properties is that when we want to express a vector in the vector space using the standard basis vectors, the coefficients of the linear combinations are the coordinates of the desired vector. Let's see an example. Here we have a vector u in n-dimensional space, and we want to express it as a linear combination of standard basis vectors in that space. So the problem is to find the coefficients in this linear combination, C1 up to Cn. But because of the properties of standard basis vectors, we know that the coefficients are coordinates of our vector.